right. So, what is important for us to understand is, of course, that cement reacts with water. The process is called hydration. The process is exothermic, it releases heat, right, and the heat of hydration depends on each individual compound that is present and also the morphology. Why morphology? Because sometimes the degree of irregularity may be different depending upon the type of processing that happens inside the kiln, okay. So, again, that is all aspects that we learn a lot more detail in cement chemistry, but for now we will not really look at that in more detail. Now, each compound has a different rate of heat evolution. As you can clearly see, your C3S and C3A evolve maximum heat. So, this heat is represented in joules per gram, okay, but this is the heat evolution or total heat evolution from reacting 1 gram of this material. This also has to be looked at from a different perspective. What is the rate of this heat evolution? Okay, 1 gram can release 500 joules, but at what rate? And that is where it is even more important to understand that C3A and C3S can liberate significant rate of heat in the early stages. And for that we need to understand the heat evolution pattern, not just from the total heat, this is the total heat, but also from the rate of heat evolution, okay, rate of heat evolution. So, this peak rate is of great significance. Why? Because in early stages, if your cement is evolving a lot of heat, your concrete temperature is continuously rising, right? Your concrete temperature is continuously rising. Even beyond, when the rate of heat evolution is low, it is still evolving heat. So, the overall heat is still building up, okay. Now, of course, evolution of heat is directly related to the amount of reaction that is happening. More reaction, more heat, okay. But this has practical significance for understanding how concrete and large structural elements is behaving. When do you release the formwork? Especially in mass concrete, this can be a quite a challenging thing to do, to decide when to release the formwork. I mean, remove the redundant formwork. Of course, the load bearing formwork you will not remove, but redundant formwork, when you remove it, you are exposing the concrete to the external environment. But at that stage, if this rate of heat evolution is still very high, your concrete inside is continuing to evolve with respect to heat, and the concrete at the surface is dissipating heat to the environment if you open up the formwork. So, what will happen as a result of this? Yeah, you will have cracking because there is a temperature differential from the core to the surface. And you will see today in many of the construction projects, this is the principal problem. All our job site specifications are written up in terms of construction that we did in the past, where we opened up the formwork at 24 hours and started curing. But for many of the mass concrete structures, this cannot be applied directly. At 24 hours could be the time where the core of the concrete is at its peak temperature. And to understand that well, you need to actually do measurements of temperature whenever you design concrete with large cross sections. Again, this is a very important part of our chapters, and we will discuss this in mass concrete. So, just some descriptions about what these peaks in the rate of heat evolution curve are, okay. As soon as you mix cement and water, there is some initial CSH formation and this heat of wetting. Any powder, right, any powder, if you wet any powder, there is an initial heat evolution. Even when you mix water into atta, of course, we can't measure that heat evolution, you can't feel it in your hand also, but still there is heat evolution. Why? Because any particle will have surface atoms which are at a high energy level. When water touches the surface, the interface that is created between water and the surface atoms has now a lower energy level. So, excess energy is released as heat, okay. Any surface will have that issue. For instance, I pour water on top of this table also, a new interface is getting created and some minuscule amount of heat is going to come out, right. So, that is the first peak, and it is usually a very high peak because it happens in a fraction of a second. We are talking about a rate, no. So, rate is going to be extremely high. Even if very small amount of heat is evolved, it is evolved in a fraction of a second. That is why the initial rate is high. Then there is a dormant period, a period where relatively lesser rate of heat is evolved. Okay, heat is continuously getting evolved, but rate of heat evolution is low in this dormant period. What is the significance of dormant period from the point of view of working with the cement? Workability, we need concrete workability at that time. If the cement starts setting and hardening, obviously we can't get workability from the concrete. So, this dormant period dictates the time that we have with the concrete, or we sometimes call it the open time, workable time of the concrete. Towards the end of the dormant period, the sudden increase in the rate of heat evolution happens and you reach what is called the main peak, where C3S leads to the formation of CSH and C3A in combination with the gypsum leads to the formation of a compound called ettringite. And then later, the reaction slows down, but still heat is continuously evolving. Okay, reaction is still happening and continuously evolving heat, the rate of heat evolution only is reducing. So, heat is continuing to build up with time. Okay. So, this happens because of continuing reactions in the longer term. You may or may not have additional peaks, but yes, there are other reactions that are continuing to happen at the longer term. Again, more specifics of hydration reactions are given. The silicates C3S and C2S, they react with water to produce CSH and calcium hydroxide. We term CSH as gel because it does not have a very well defined crystalline structure, nor is it completely amorphous. It is a in between phase, that is why we call it gel. Okay. Gel is basically a representation of a colloidal system, but more or less this is what the CSH structure is like. The more C3S that you have, the more calcium hydroxide you produce. So, 3 times as much calcium hydroxide is produced by C3S hydration compared to C2S. We talked earlier that a pozzolan has reactive silica and this silica combines with calcium hydroxide to produce CSH. So, in a high C3S system where more CSH is available, your possibility of pozzolanic reaction is going to be more C3S, more C3S, more calcium hydroxide, more available lime for pozzolanic reaction, right. CSH again, just like other cement chemistry terms, it is also written very loosely as C-S-H. It does not have a very clear cut formulation, but within the structure of CSH, the calcium to silica ratio varies from 1.5 to 2, 1.5 to 2. Okay, that is the typical nature of CSH. The aluminates, in the absence of gypsum, you form rapid hydration of aluminates happens to form calcium aluminate hydrate. What is this phenomenon called in the absence of gypsum? Flash setting, right? Flash setting, when the aluminates immediately react with water and do not really have a controlled rate of hydration. Okay, in the presence of gypsum, the aluminates will react with the sulphate to form ettringite and monosulphate depending on the overall composition that you have in your system. Ettringite formation causes expansion. Now, in the early stages of cement hydration, when concrete is still pliable and moldable, this expansion does not have any problem. But imagine if this reaction happens in the long term, if your concrete is sitting in a soil that is rich in sulphate and that sulphate enters concrete and reacts with the aluminates to form ettringite, what will happen? Expansion and then cracking, right? Expansion will lead to cracking. So, if sulphate rich soils and waters are present, then you need to avoid this ettringite formation in the long term. That is why sulphate resistant cement has low C3A. So, lower aluminate implies lesser possibility of ettringite formation. Again, I am not delving deeper into this set of reactions. You do not have to remember the chemical formulation and all that. Okay, this is just for your benefit to understand that you have various sets of reactions possible. Again, these are approximate reactions, these are not exact. Okay, so this is just for the purpose of balancing the equation that very nice complete reactions are written. It is not always like this. So, ettringite is a very interesting structure. This is ettringite. You can see here that it's got a large amount of water of hydration. H is H2O. Okay, H is not hydrogen, H is water. So H32 means 32 molecules of water are bound in the structure of the ettringite. Similarly, CSH has water bound in its structure. So what will happen when you heat cement paste? When you heat concrete, what will happen? What's going to happen to this water? It's going to get removed, right? When you take cement and mix it with water and hydrate it, all these products are formed. The same cement paste, if you heat it, you will slowly evolve the water, release the water that is present. Okay, it just so happens that the water released from these products happens at different temperatures. So CSH, the water loss is at less than 300 Celsius. Ettringite, around 100 to 120 Celsius, you will lose all the water. Okay, calcium hydroxide, you lose the water only between 450 and 500 Celsius. Okay. So, this is a very important technique for us to understand the overall composition of your cement or cement paste, which is called thermal analysis. All you do is take your material and heat it to different ranges of temperatures. So, what happens to concrete in the case of fire? This is what will happen. As the temperature increases, the different phases will dehydrate. But why does spalling happen in fire? Why does spalling happen? I mean, why should dehydration cause spalling? What? Moisture basically is trying to come out through the fine pores, right? It converts to steam. So, water expands when it converts to steam. It's trying to come out rapidly through the pores, and that causes the spalling. Okay. So, overall concrete deterioration will occur over a large temperature range, but spalling may start quite early. Okay. So, this is the evolution of hydration products. As hydration proceeds, the maximum amount of the compounds available is for CSH and calcium hydroxide, which is only expected because most of your cement is silicates. When silicates react, they give you CSH and calcium hydroxide. The aluminates, the ettringite that forms slowly converts to this phase called monosulfate, okay, and much of the ettringite has already converted by the time significant hydration actually takes place. And you may also form other aluminate hydrates. Okay. So, just to look at the, okay, this is again another picture of what happens with the formation of these compounds over the long run. Now, if you look at this picture here, it just tells you that in the early stages, the cement particles are dispersed in water. Cement particles are dispersed in water. Only at the edges of the cement particles, there is hydration happening. Only at the top surface of the cement particles. As hydration proceeds, more and more of the particles start dissolving outwards, and you get an increase in the amount of hydration products forming. So, as a result, what is happening to the space in between? What is happening to the space in between? It is continuously reducing. The water filled space is continuously reducing. So, in other words, as hydration proceeds more and more, the porosity will continuously reduce. Now, in the beginning itself, if I had more cement in the system, if I put more particles of cement in the system, what will happen? Sorry? No. Just look at it from this perspective. I said as continued hydration reduces porosity. In the beginning itself, I have a lot of cement in the system. That means I am choosing a low water to cement ratio, right? When I choose low water to cement ratio, that means the space occupied by cement is now higher than in a high water cement ratio mix. So, what happens then? Heat liberation, yes, that is going to happen. More cement means more heat, no doubt. There is lesser space available now for the hydration products to form. In other words, my porosity reduction starts happening very early, right? My porosity reduction will start happening very early when I have more cement present. Now that also means that possibly in the long term, I may not have sufficient space for hydration to happen at all. What does that mean? Again, incomplete hydration. As I lower the water to cement ratio, I get lesser and lesser hydration. Now, this is counterintuitive, no? We always think that when we want more strength, we want to reduce the water cement ratio. But now I am telling you that when you reduce the water cement ratio, the possibility of hydration also goes down. What's happening here? So, what is strength dependent on? It's dependent on hydration, but we just said that when you lower water cement ratio, you get lesser hydration. So, why does strength increase? Okay, particle packing is going up, but is that the only thing? Particle packing, yes, but what is happening essentially is your porosity reduction is much more rapid in lower water cement ratio systems. Strength is dependent on porosity. The higher the porosity, the lower the strength. Okay. So, this explains two things for you. One is in low water cement ratio systems, you have lesser porosity, so higher strength. At the same time, in low water cement ratio systems, there is less hydration happening. That means what? That means you have a lot of cement that is sitting there as what? Cement is sitting there as what? As a filler, exactly. Cement is sitting as a filler. Now, why do you want to waste cement as a filler? Right? So, this is another case to understand the utilization of supplementary cementing materials or mineral admixtures. Why do we want to waste cement as a filler? You could as well replace it with supplementary materials. Okay, so it's important to understand from the overall perspective. Now, that doesn't mean that we don't cure concrete with low water cement ratio, because hydration is only less. Why bother curing? It's not correct. There are other problems with it, which we'll talk about when we talk about high strength concrete. Okay, again, this is just showing you the rate at which the properties of the cement or concrete develop, right? You have porosity reduction, you have permeability reduction. Why does permeability reduce? Porosity reduces. Why does permeability reduce? Why? Because the connection of the porosity also is reduced. With more hydration, porosity reduces and the connectivity of the porosity also reduces. That is why permeability goes down. This is the reason why we do curing. We want to do curing to ensure that the porosity and permeability reduce in the system. Okay. And obviously, when the porosity is coming down, the strength is going to go up. Of course, in the beginning, when the concrete is not set yet, there is no real meaning to strength. Only after the setting is completed, the strength development is really taken into account. Right, just to show you very quickly structure of hydration products, your CSH is basically these loosely defined structures. The well-defined crystalline structures could be that of ettringite, right? The large crystalline components could be that of calcium hydroxide, okay? Large crystalline components are calcium hydroxide. Another picture of showing the fibrous, loosely gel-like defined nature of CSH. More pictures on CSH. Calcium hydroxide, as I said, is well-defined crystalline phase. It's got a hexagonal crystalline shape, and because of its well-defined bulky shape, it's got a low surface area. CSH, on the other hand, as you can see, because of its fibrous shape, it's got a very high surface area. So, when you convert your calcium hydroxide to CSH, your ability to occupy porosity increases. What does that mean? Now, if I have a pozzolanic reaction, I am converting calcium hydroxide to CSH. That means more and more pores can now start getting blocked by CSH. That is the reason why durability goes up when I use pozzolanic materials, because your pores become finer and finer. As your pores become finer, water or other chemicals cannot easily enter the porosity. Permeability reduces. Okay, we will come back to that subject, of course, later. Ettringite, monosulfate, these are all highly crystalline components. You can find these distributed across the overall microstructure. Again, more pictures of ettringite and monosulfate. These are all taken with the help of scanning electron microscopy, because you need the resolution defined by SEM to really get to this level. Optical microscopy cannot do this extent of imaging. So, this is very important. What is the nature of porosity in concrete and porosity and air voids in concrete? So, if you take a scale all the way from 10 millimeters to 0.001 micron or 1 nanometer, various features within concrete are at that range. So, obviously, in this range you have your aggregate, right? Your fine aggregate is up to about, okay, this range, fine aggregates will come all the way up to about 150 microns, right? And coarse aggregates are 5 millimeters and more. Entrapped air voids. So, you mix concrete, you vibrate it, but it is not possible to completely eliminate all the air from the mixture. So, some air will get trapped, right? Some air can also get trapped because of bleeding. What is bleeding? Water rising to the surface because it is lightest in weight. Sometimes it may get trapped under the aggregate and lead to a formation of a what we call as a bleed lens, and that is exactly later going to become a void. Okay. But that is not an air void, it is a bleed lens, but nevertheless it will be of the same size as a typical entrapped air void, several millimeters in size. And then you have entrained air bubbles. What is entrained air? Air that is wantedly introduced into the system because of performance in specific environments like freezing and thawing, right? You put in these chemical admixtures which will entrain air, we will talk about that later. The size of the entrained air bubbles you can see is from several tens of microns up to about 1 millimeter, right? Then in cement paste itself, the hydration products could be at different scales. Your calcium hydroxide crystals are of the order of a few microns. Aggregation of CSH particles, again of the order of a few microns. Your capillary voids are from 1 micron all the way up to about 10 nanometers, the large range for capillary voids. What is capillary void? It is the voids present within the cement paste. Capillary voids are not the same as entrained or entrapped air voids. Capillary voids are capillary pores. These are pores, okay. Pore is basically more of a long continuous void that exists within the paste, whereas entrapped and entrained air voids are more discrete voids that are present, okay, whereas capillary voids are more called capillary pores, okay. If you go still further, the interparticle spacing between CSH sheets is of the order of few nanometers. So, this range is what is called gel pores. The pores that is present within the CSH gel pores. These are capillary pores and then you have gel pores. So, the sizes of your air voids and porosity within your system are varying significantly all the way from 1 nanometer to several millimeters. So, this heterogeneity is what makes concrete very complicated. This heterogeneity is the problem, and because of which we are not able to perfectly predict the properties well enough. Now, just this is a easy review in terms of properties of concrete. Workability, you know very well, is defined as the ease of mixing, placing, compaction and finishing. There is no single test that measures all of these aspects, right? We use slump test, but that is not really giving you a complete picture. A concrete having a good slump need not be a concrete that can be pumped easily. Usually you can design mixtures in that way, but it need not always be correlated. So, there are different ways of testing workability, but nobody bothers about compaction factor anymore, of course, right. But for stiffer mixtures, you can use the flow table test or the VB test for stiffer mixtures, because slump cannot be measured, slump is 0 for stiff mixtures. So, you can use the flow table or the VB test. Your IS guidelines give you some correlations between what you can get for different types of mixtures in between these tests. But these days, all of this is actually almost going out of the window, because more and more people in job applications are shifting towards flowable concrete, right. There are of course applications where zero slump concrete is also required, for instance roller compacted concrete, but most applications involving concrete and regular structures is moving towards self-compacting concrete because it eases the application significantly. Now, placement of concrete, it has to be done directly in position rather than heaping it in one location and trying to rake it, because you don't want to cause any segregation, right. So, you need to ensure that concrete is poured almost vertically down rather than coming at an inclination, again to avoid segregation of the aggregate from the concrete. So, again segregation and bleeding need to be paid attention to. Segregation is simply separation of paste and aggregate. Bleeding is separation of water from the mix. All this happens when you don't design your mix well. Sometimes when you over vibrate your concrete also, it can happen. When you over vibrate, you can lead to segregation and bleeding. Of course, vibration is absolutely important from the point of view of obtaining right compaction level in the concrete, because if you don't compact well, you don't get the properties that you have. You have different types of vibrators, external, internal, surface vibrators, formwork vibrators and so on and so forth. Finishing follows compaction, and there are various ways of finishing. These days of course, finishing is leading to an entirely new science of concrete technology, that is textured concrete, right. You get a lot of textured concrete. In fact, now texturing has reached the level of actually even putting photographs on the surface of concrete, just like what they do on the top of cakes, right. Icing on the cakes, just like that they have icing on the concrete with people's photographs also can be on top of the concrete. So, all of these are very specific specialized applications of concrete today, but there are various different tools that are available. We will talk about some of these tools and their significance when we actually deal with certain aspects of how concrete with mineral additives needs to be looked at very carefully with respect to finishing operations. Just to show you some pictures, I am sure most of you have had experience with using some of these equipment. And of course, curing of concrete, it is important to obtain the required level of hydration, but from the point of view of curing is done not so much for strength, but more for durability. Always remember that curing is important for durability. Now, a lot of people seem to think that concrete is cured on the site to keep the concrete temperature low. It is not correct. You don't want to pour cold water on top of a hot concrete. It's a bad idea, right? So, that is a false idea in the minds of people who are at the site. They think that they keep temperature low by pouring water. It's not the idea. The idea is to ensure that moisture source is available to ensure that concrete does not dry out during the process of hydration. Various methods of curing. An important discussion obviously which will come later is the use of membrane forming compounds or curing compounds that are applied in many job sites nowadays, because water for curing is not easily available.